Okay guys, I've started the practice session for chemical bonding. We're done with this chapter. Only watch this practice session after you are done with watching all the recorded classes which you've missed or which you've yet not watched of the live session, right? So please complete the entire chapter before attempting these questions because you won't understand most of it if you've not watched the lectures, right? And you guys will see how easy things are. After you go over these questions, you guys may even, tell me that, Sir Suleiman, why did you make us cover everything in so much detail? It's because the theory is very easy. It's the MCQs which will test your concepts. Even the MCQs are easy, but if your conceptual understanding is up to mark, right? So the reason why I've taught you guys the entire chapter in so much detail is in order to enable you to be very confident in the MCQs. I'll do the MCQs with you as well. Don't worry about that, right? For now, I just want to show you how easy the theory for chemical bonding is. It's largely O levels and IGCSE, right? Chalo, let me show you. It says the group 14 elements show a change from non-metallic to metallic character down the group. Table 3.1 shows some properties of two group 14 elements, carbon and tin. In their standard states, the table is incomplete. It says complete table 3.1 and it's for 3 whole marks. 3 marks to complete table 3.1. What is the electrical conductivity of graphite? We know that graphite is a good electrical conductor. So because good is written on the right hand side, I'll write good here as well. Electrical conductivity good for tin. It's also good for graphite because it has delocalized electrons which are free to move. Yeah. I'm saying what's the type of bonding? So tin has metallic bonding. What is the type of bonding in graphite? It's covalent bonding. It's a giant molecular structure. And easy. Now, type of structure. This is a giant structure. Tin is a metallic lattice, and metallic lattices are giant metallic lattices. Easy. 3 marks for nothing. 3 marks for O-level stuff. Identify the lattice structure shown by graphite. What's the lattice structure shown by graphite? It's called what? It's called the giant molecular lattice. That's the lattice for it. Giant molecular lattice. That's the lattice structure, sir. Or giant molecular structure. Explain why tin has good electrical conductivity. Well, tin is a metal. And if it's a metal, it'll have delocalized electrons. And if you have delocalized electrons which are free to move, you're going to conduct electricity. So, SN has delocalized electrons, but don't just write delocalized electrons. That's not the explanation. It has delocalized electrons which are free to move, because we realized that in Buckminster fullerene there were delocalized electrons but they weren't free to move. So you need to tell the examiner, hey, tin has delocalized electrons which are free to move, and that is the reason why it can conduct electricity. Again, how easy. The entire 5-mark question out of your 60-mark paper. Figure 3.2 shows the boiling points of the simplest hydrides. Hydrides are just hydrogen bonded to group 6 or group 14. Hydrogen bonded to other elements is called hydrides, right? That says he's shown you hydrides of carbon to lead. And explain the trend in the boiling point of group 14 hydrides shown in figure 3.2. Now, what is the trend? The trend is pretty simple. You'll see that the trend is that the general trend is what? That there's an increase in boiling points. There's an increase in boiling point from CH4 to PbH4. So I'm going to tell the examiner, hey, first of all, let me show you the trend. There's an increase in boiling point from where to where? CH4 to PbH4. Now I say explain it as well. We know that the increase in boiling point depends on the number of electrons. They're all going to depend on the number of electrons, right? Electrons, right? So we're going to talk about the number of electrons. So why would there be increase in boiling point from CH4 to PbH4? It is because due to a higher number or due to more number of electrons. And when you have more number of electrons, what's going to happen? You're going to have larger dipoles and therefore stronger van der Waals. Stronger van der Waals. Stronger van der Waals due to what? Remember, electrons have an impact on the ID-ID interaction. So stronger van der Waals due to ID-ID interactions. or you could say stronger van der Waals due to instantaneous dipoles and induced dipole forces, stronger in van der Waals due to London forces, stronger London forces, stronger dispersion forces. You could also say stronger London forces, or dispersion forces. All are the same thing, right? And therefore, what's going to happen? Therefore, more energy is required to boil it. These are 3 marks. More energy is required to overcome these bonds, to overcome these van der Waals effectively. Not bonds, these van der Waals. Done. That's it. Easy stuff, huh? Easy stuff for 2 marks. Yes. That's the trend. Why? Due to more number of electrons as you go from CH4 to PbH4, and more number of electrons means stronger van der Waals due to ID-ID interactions, or you could say due to London forces, dispersion forces, and therefore more energy is required to overcome these WdV, van der Waals forces. Right? Deduce the shape of SiH4. Now it's in group 14. He's even told you this. See, Si, these are all group 14 elements. Group 14 or group 4 means that it's going to have 4 electrons in its outermost shell, and if it's making 4 bonds with hydrogens, that means that it's utilizing all the 4 electrons. It's utilizing all the 4 electrons. It's what? It's a tetrahedral shape right here. Tetrahedral. 109.5 is the bond angle. There's no lone pair. How easy. Literally, this is your paper. SiO2 is a white solid that melts at 1700 degrees Celsius. Why? SiO2 is a giant covalent molecule, right? It's a giant molecular structure. GM. Giant molecular structure. What is there with giant molecular structure? Giant molecular structure has strong covalent bonds. Strong covalent bonds. Remember, it has strong covalent bonds. It's a giant molecular structure, and therefore a lot of energy is required to break these covalent bonds. Whereas SiCl4 is a colorless liquid at room temperature and pressure. And that means what? At room temperature, if it's a colorless liquid, this indicates the fact that it is a simple molecular structure. I know this is not a giant molecule, and even the further he's saying that it's a liquid at RTP, so it can't be a giant molecular structure. It's what? It's a simple molecular structure. And because it's simple molecular structure, it has weaker forces, which we call weaker intermolecular forces of attraction. So these forces can easily be overcome compared to the strong covalent bonds. Now I'm saying explain the difference in melting points of these 2 compounds with reference to the structure and bonding. So SiO2 is a giant molecular structure with strong covalent bonds. Whereas what? Whereas SiCl4 is a simple molecular structure. How did I know it's a simple molecular structure? Because it's a liquid at RTP, right? It's not a solid, it does not have a high melting point or whatever. So it's a simple molecular structure, and so less energy is required to overcome the weak van der Waals, or to overcome the weak intermolecular forces of attraction, IMF. You could have also just said to overcome the weak van der Waals, because you realize it will not have hydrogen bonds, right? It'll only have PD, ID, and in this case it would only have ID, because there is symmetry. It's a non-polar molecule. See, it's a non-polar molecule because you could see a symmetry between this shape. Yeah, SiCl4 is a tetrahedral shape. All 4 atoms are identical at all 4 ends, so it's a non-polar molecule. But hey, I could play it safe and write intermolecular force of attraction, right? So SiO2 is a giant molecular structure with strong covalent bonds, whereas SiCl4 is a simple molecular structure, so less energy is required to overcome the weak IMF of SiCl4, versus to break the bonds, versus breaking the bonds of SiO2. Bonds, not IMF of SiO2. Draw the dot and cross diagram to show the species present in Al2O3. Draw the outer electrons only. So if you look at Al2O3, what in the hell is this? It is aluminum 3 plus ion, 2 aluminum 3 plus ion being bonded to 3 oxide 2 minus ion, right? You must have studied this in O levels and IGCC. Al2O3, 2 aluminum ions, 3 oxide ions, right? So what happens? He's saying just show me the species, show me the diagram to show the species present in Al2O3, the outermost. So aluminum, it loses 3 electron, it has a charge of 3 plus. I don't need to make make circles. I don't. It had 3 electrons in its outermost shell, lost all 3 electrons. All 3 electrons were transferred to oxygen, right? So aluminum loses all 3 electrons, and what happens to the O? I just need to draw one aluminum ion and one O. What happens? O was already 6 electrons, and it got 2 electrons from the aluminum right here, and it has a charge of 2 minus. That's how it would look. That's it. Al has a charge of 3 plus, O has a charge of 2 minus. That's what I'm going to do. Remember, I told you not to draw these circles. No need to draw these circles. Sir, where would the third electron go of aluminum? Well, if you want to make it completely, complete look of this would look something like this. You would have 2 aluminum 3 pluses, and you would have 3 O's, and this is how it would look. But you just need to make this. That's it. That's all you require to make. That's all that is required in the exam. You don't need to make all 3. To show the species. You could also make something like this. That's 2, that's 4, that's 6, and has a charge of 2 minus, 2 minus, 2 minus, and see, this in total lost 6 electrons. It gave 2 here, gave 2 here, gave 2 here. Boom, that's it. But in the exam, this would also do the job. That's it. Yeah, easy. Next. Figure 2.1 shows the boiling points of H2O and other group 16 hydrides. Hydrides are just hydrogens bonded to other elements. Right? So H2O is the anomaly. Why is this the anomaly? You should know this because of hydrogen bonding. Yes, sir. So it's saying explain the trend in boiling points of group 16 from H2S to H2TE. Just explain this trend. Don't talk about H2O. Just explain this trend. What's this trend? Well, I know that the boiling point is increasing. Why is it increasing? Because the number of electrons increases, and number of electrons increasing means larger dipoles and therefore stronger van der Waals due to ID-ID interactions or stronger London dispersion forces, right? So I could say, hey, from H2S to H2TE, they have the electrons increase. So from H2S to H2TE, the number of electrons increase, which means larger dipoles, and therefore larger dipoles means what? Therefore stronger van der Waals or stronger London dispersion forces, or stronger London forces. It doesn't really make a difference. Dispersion forces. Yes, and therefore the boiling point increases as more energy is required to more energy is required to overcome them. So more energy is required to overcome these forces. Right? How easy. अब बताएं क्या मुश्किल है. Explain why the boiling point of H2O is much higher than H2S. Why? You tell me why. Why? Because there's a hydrogen bond, right? There's a in H2O. See, in H2O you have hydrogen bonding, you have PD-PD, and you also have ID-ID. Whereas here you have, between these three, you only have PD-PD and ID-ID. They're all polar. These are all polar, right? Because they're all bent molecules. So you have PD-PD and ID-ID here. So the hydrogen bonding right here, the hydrogen bonding and the hydrogen bonding that you have right here is much stronger than all the other intermolecular forces of attraction, right? That's it. So therefore, only H2O has hydrogen bonding. So I'll tell the examiner, hey, only H2O has hydrogen bonding, which is much stronger than the other intermolecular forces which exist in H2S. Easy. बस और बताएं. Suggest the shape of AlOH minus. Remember, when you have an ion, how do you select the shape? Well, you have to look at the central atom. Aluminum was in group 3. This minus means that we're going to assume that the aluminum has gained an electron. So now aluminum has 4 electrons and it's bonded to 4 OHs. So no lone pairs, right? Aluminum has 4 electrons and is bonded to 4 OHs. No lone pairs. So what does that mean? That means it's what? It's tetrahedral. That's it. That's the shape for it. If you were to ask to draw it, that's how it would look. So it's what? Tetrahedral. अब बताएं, आसान है मुश्किल है. Nitrogen, phosphorus are elements of group 15 of the periodic table. Complete 3.1 to show the properties of nitrogen and phosphorus in their stranded states. So nitrogen is also a simple covalent molecule. Phosphorus is also a simple covalent molecule, right? So you're seeing electrical conductivity of nitrogen. Nitrogen is a simple covalent molecule, does not conduct, has no delocalized electrons which are free to move. Poor. Now, type of bonding. Type of bonding in nitrogen and phosphorus. What's the type of bonding? Both are covalent. That's it. Covalent, covalent. Easy. Type of structure. What's the structure? It's a simple structure. And what is phosphorus? Is also a simple structure. Effectively, same thing. Done and dusted. A form of solid nitrogen has a lattice structure similar to solid iodine. So he's saying that N2 looks just like I2 solid. There again, there's still simple molecular structures. Identify the type of lattice structure of solid nitrogen. What type of lattice structure is this? Just like you called graphite as a giant molecular structure, this lattice structure would still be a simple molecular structure. Simple molecular lattice. Yes, that's the structure. At very high temperatures, phosphorus can form P2 molecules. P2 contains P triple bonded to P. Describe the formation in terms of orbital overlap. What's the orbital overlap? The first orbital overlap would be a sigma bond. The second orbital overlap would be pi bonds, right? The second and the third. So we know it has one sigma, two pi's, and this sigma bond takes place because of the P and P orbital head-on overlap. There's a head-on overlap between the P and P orbitals, and in this case there is a sideways overlap between the P orbitals, right? The P and P orbitals. And in reality, we should know the fact that, these are hybrid orbitals. The sigma bond that is going to form is because it's going to be is due to the hybrid orbitals. It's going to be the sp hybrid orbitals. But even if you write the P and P overlap, it's fine. You could either say it's the head-on overlap of the P orbitals, or you could say it's the head-on overlap of the sp orbitals. It's sp hybridized, because it is one sigma, two pi's, which means that out of the three p bonds, out of the three p orbitals, two are going to be unhybridized and one is going to hybridize with s to form the sp orbital in order to form this sigma bond. So let's talk about it. What's the formation? The formation is that, there is one sigma and two pi bonds. Here you go. That's the description. Secondly, there's a head-on overlap. There's a head-on overlap of the p orbitals, or you could say the sp orbital. Doesn't really make a difference. The sp orbital, which makes the sigma bond, and there is a sideways or side-on. It's also called side-on overlap. Side-on overlap. Head-on, side-on, right? But sideways is also correct. Sideways ho gaya, lateral ho gaya. So sideways overlap of the p orbitals. Forming the pi bonds. Please don't stress a lot on the marking schemes. Marking schemes are meant for teachers. You have to write these descriptions. You have to talk in terms of concepts, not in terms of, bas marking scheme mein 2 lafz likhe hain, so I'm just going to write 2 words. No. You have to write stuff like simple molecular lattice structure. I don't know if you want to add this here, if you want. The bond energy of the P triple bonded to P is 485 kilojoule per mole. The bond energy of N triple bonded to N is 944 kilojoule per mole. It's saying compare the reactivity of P2 and N2, explain your answer. Now, although I've not taught you guys this chemical energetics, but the reason why I've added this question here is because it's pretty logical. He's saying in order to break these bonds and make them react, you need this much energy. In order to break these bonds and make them react, you need this much energy. Which one will be more reactive? Obviously, P2 is more reactive because you require less, it has less bond energy. So you can break these bonds easily and make them react. That's it, easy. So because the P triple bonded to P is a weaker bond, it's weaker, so it is more reactive than N triple bonded to N. And he's shown it to you right here. 485 and one is 944. Pretty easy. 1 mark. That's easy. A dot and cross molecules of SCl2 contains a molecule of SCl2 contains two SCl covalent bonds. Complete the dot and cross diagram to show the arrangements of the outermost electrons in SCl. And he's shown you that it contains SCl bonds. So SCl2 would look like what? SCl bonded to Cl. But again, sulfur is in group 6. If it makes two bonds here, it has two lone pairs left. And these two lone pairs are going to push on it. So it's not a linear structure. It looks something like this. Always draw the proper structures for yourself. It's a bent shape. It's a V shape or a bent shape or a non-linear structure, right? Now, he's saying complete the arrangement, show dots and cross. You know that a bond represents a pair of electrons. So represent a pair of electron and a pair of electron. How many? You have one lone pair and one lone pair left here. So one lone pair and one lone pair. And chlorine is in group 7. It shared one electron here. It has 6 more electrons left. 2, 4, 6. 2, 4, and 6. That's it. Now I think predict the shape of and the bond angle of the molecule using the VSEPR theory. What's the shape and what's the bond angle? Again, the shape is a bent shape. You could also call it a non-linear shape. You could say the shape is bent. You could call it angular. You could call it non-linear, V-shaped. You could also call it not. It doesn't matter. Non-linear we कह सकते हैं. Doesn't matter. You could call it either or, right? And what's the bond angle? Well, if these lone pairs did not exist, it would be tetrahedral 109.5. If one lone pair exists, it would have been 107. And if two lone pairs exist, it's now 104.5, just like in water. It's 104.5. Done. That's easy, huh? Degrees. Oh, I would have gotten a mark deducted. That's how crucial A levels is. I need to put on the degree sign as well. Degrees. That's how crucial A levels is. If you just wrote 104.5, maybe you wouldn't have gotten the mark. Boron nitride is a white solid that melts above 2900 degrees Celsius, which kind of is an indication that it's a giant molecular structure. It shows, figure 2.2 shows part of the lattice structure of a crystal of boron nitride. Okay, good stuff. It looks like graphite, doesn't it? Use figure 2.2 to deduce the empirical formula of boron nitride. You'll notice that he's given you boron atom and nitrogen atom. And if you notice, each boron atom is bonded to a nitrogen atom, then a boron is now added to nitrogen, boron is added to nitrogen, boron added to nitrogen, boron added to nitrogen, boron added to nitrogen, boron. It's just a B being bonded to N. That's the ratio. It's just one B and one N. You might think that, hey, this nitrogen atom is being bonded to two borons, but in fact you need to understand that this nitrogen is being bonded to this boron, and then this boron is being bonded to this nitrogen, and this boron, it's just strong bonds right here, strong and strong bonds. Or what you could have done is, if you get confused in these things, you could look at each of these on its own. You could see, hey, one white ball is attached to 3 black balls, right? One white ball is attached to 3 black balls. But also look at the black ball. Each black ball is also attached to 3 white balls. Each black ball attached to 3 white balls. Each white ball attached to 3 black balls. So it's just 1:1. That's pretty simple. That's logical. They wanted you to deduce the empirical formula from logic. So Bn, boron nitride, that's the empirical formula for it. I even taught you guys this in the last class. Suggests the identity of another crystalline solid that has atoms arranged in layers similar to that of boron nitride. That's graphite. Literally, it looks exactly like graphite. Done. That's the identity for it. Next. Hydrocarbon molecules contain covalent bonds. Define covalent bonds. What is covalent bonds? It's electrostatic force of attraction between what and what? Electrostatic force of attraction between nuclei of two atoms and its shared pair of electrons. Yes. Done. A C double bonded to C bond in an alkene is made from sigma bond and pi bond. Identify the hybridization of the carbon in an alkene. We know from a little bit from our O levels in IGCSE that alkenes are what? They look something like this. Carbon double bonded to carbon, and each carbon has two hydrogens. What structure is this? Is trigonal planar. Uno, dos, tres. That's the trigonal planar structure of each carbon atom, right? That's the trigonal planar structure. And we know if you have a trigonal planar structure, no lone pairs, that's sp2 hybridized. So it's what? It's sp2 hybridization. That's it. Draw label diagrams to show in terms of orbital overlap how the sigma and the pi bonds are made in carbon double bonded to carbon. So we know carbon is in the p block, right? So it'll be the p block overlapping in a head-on manner with the other p. It will be the p orbital overlapping with the other p orbital in a head-on overlap, and this one would be a sideways overlap. So he wants you to show the orbital overlap, right? So let's show the orbital overlap. I've shown it to you. You know, it would look something like this. Uno. Oh my god, pathetic, Suleiman, pathetic. You know, you guys should be good with your drawings. You know, you guys should be a little better. Make sure that the sizes are similar. My god. God knows how I got my marks when it came to these questions. You know, this is how it should look. Again, I would probably get a mark deducted because this is pathetic, but try to make it as, you know, as close to each other as possible. You get the idea, right? So that's the head-on overlap. That's one. And make sure that, see, the overlap, the shade pair lies along the internuclear axis, between the internuclear axis, right? But for a pi bond, we know it's a sideways overlap. So it would look something like this. You know, something like this. Just make sure that these two points right here, they are the same, and these two are the same. See, this seems a little shorter, so probably I may not get a mark for it, but you guys have to draw it in a better manner. And if you guys struggle showing the orbital overlap, you could even show the kidney bean structure. Like if I struggle, oh my god, pathetic, Suleiman. Again, pathetic. Okay, this is better. My god, this is like this. And then how do I show the kidney bean structure? Right here. My drawing is pathetic. So that's how you could show the overlap like this. So either you show the, although when they're asking specifically for orbital overlap, I guess you should make this. It's far better. In the exam, both are acceptable. You know, when I showed you that they say, show me the pi bond. If you want to show the pi bond, then this is the better way of doing it. But if they say, show me the orbital overlap, then this is the better way of doing it, right? But that's up to you, whatever you want to do. In electrophilic reactions, I don't know what electrophilic reactions are for now, but they involve the pi bond of C double bonded to C is broken. Okay. Suggest one difference between the sigma and the pi bond that explains why the pi bond is broken in these reactions. Why would the pi bond be broken quickly compared to the sigma? Why isn't the sigma bond being broken? Why is the pi bond being broken? Why? Because the pi bond is weaker compared to the sigma bond. Pi bond is weaker. And why is it weaker? Why is the pi bond weaker versus the sigma bond? Why? Why is it weaker? Because in a sigma bond, the pair of electrons that you have, they are closer to the two nuclei. Whereas in the pi bond, the pair of electrons that I have, they're above and below the two nuclei. It's above and below the internuclear axis, which means it's farther. Therefore, weaker attraction for a pi bond compared to a sigma bond. Stronger attraction in sigma bond. So if sigma bond is weaker than, pi bond is weaker than a sigma bond. Why? Because sigma bond has stronger attraction as the electrons, the shared electrons, are between the two nuclei. Are between two nuclei. Right? Stronger attraction. Shared bonds are between two nuclei. Sir, for 1 mark, should I write this much? Yes, please. It's A levels. It's not O levels. You need to tell the examiner that you know everything about this. I know stuff. You know, or you could have even talked from the perspective of pi bond. You could have said, hey, pi bond is weaker versus sigma bond because in a pi bond, the electrons are for the shared pair of electrons are further away from the nuclei, so weaker attraction. You could have talked about the pi bonds from the perspective of pi bonds as well. You know? State and explain the difference in ionic radius of Al3+ compared to Mg2+. So first of all, let's state the difference. For this, first of all, write the electronic configuration. Always have the periodic table at your disposal. So let me add the periodic table to write the electronic configuration first, and then let's kind of discuss this question. It's a good question. Okay, if your concepts are clear, you will never get scared of any such sort of question. You know, Mg2+ and 3 plus, right? Let's talk about this. So aluminum has the electronic configuration 1s2, 2s2, 2p6, 3s2 and 3p1, right? 1s2, 2s2, 2p6, 3s2 and 3p1. That's aluminum right here. And magnesium is what? Magnesium is 1s2, 2s2, 2p6, right here, 2p6, and it's 3s2, right? 3s2. Now, if it's magnesium 2 plus, that means it's going to lose these 2 electrons. So it's 1s2, 2s2, 2p6. And if it's aluminum 3 plus, it's going to lose these 3 electrons. These two now have the same electronic configuration. And if they have the same electronic configuration, that means they have the same shielding. They both have the same shielding effect, right? But the beauty is that although both have the same shielding effect, aluminum has a greater what? Has a greater nuclear charge. How do I know aluminum has a greater nuclear charge? Aluminum has 13 protons and magnesium only has 12 protons. Furthermore, aluminum is also smaller because for the same electronic configuration, it has a 3 plus charge. 3 plus means it's now tightly held. It has aluminum loses 3 electrons and magnesium loses 2 electrons. So aluminum is smaller. Why? Because it has more proton, greater nuclear charge. So if I were to compare the sizes of the two, aluminum is smaller because the outermost electron, the 2p6 electrons, are being pulled by 13 protons, and in this case the 6 electrons are being pulled by 12 electrons. So which one would be smaller? Obviously aluminum would be smaller, greater nuclear charge. So I'm going to tell the examiner, hey, what is the ionic radius? If I were to state them, aluminum 3 plus is smaller than Mg2 plus. Always write the electronic configuration, it'll show you everything. So aluminum 3 plus is smaller compared to Mg2 plus. I'll write it here, versus Mg2 plus. And what could be the reason for it? Let me explain it to you. Well, aluminum 3 plus has a greater nuclear charge. Why? Why does it have a greater nuclear charge? Because it has more number of protons, as higher protons, which are 13, versus magnesium, which has 12 protons, right? And also, what about shielding? Well, sir, shielding is the same for both. So SH, there's always an I before an E, right? So shielding effect remains the same for both. So effectively, what is happening? The shielding effect is remaining the same for both. Aluminum has greater attraction for greater nuclear charge, greater attraction, and therefore what's going to happen? The effective nuclear charge of aluminum 3 plus is higher, right? If the shielding is constant and you have a higher nuclear charge, we know that something known as effective nuclear charge would be higher. So aluminum 3 plus has a higher effective nuclear charge. Yes? Done and dusted. For the remaining electrons, obviously, or a greater nuclear pull for the remaining electrons. There are fewer electrons compared to protons. Easy peasy. Draw a label diagram to show the bonding in sodium. Sodium is a metal. How do you show the bonding? It's pretty easy. 1, 2, try to make them as close as possible. 3, 4, 5. I'll show you layers. 1, 2, 3, 4, whatever. Always show 3 layers. 3, 4, 5, whatever. Right? So it's negative, negative. These are not negative ions. I'm adding negative sign. These are all pluses because sodium is, in group 1. Plus, plus. These are the lattice of positive ions. And these are my negative charges. Negative, 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 delocalized, all here, here. Yeah. So I'll also using label diagram. So these are positive ions. And these are delocalized electrons. This is a label diagram. 1 mark for this. Easy, huh? Easy. C of delocalized electrons effectively. SCN minus is colorless. Complete the dot and cross diagram in figure 3.1 to show the arrangement of the outermost electrons. Now, this is the D part. Maybe in the A part or in the question, they should have shown you the structure for it. But I'll tell you how it looks. It's C triple bonded to N and single bonded to S. Now, can you write the dot and cross diagram for it? Absolutely, I can. Because each bond represents a pair of electron, a pair of electron, a pair of electron, right? And also, please understand that carbon is in group 4. It has made 4 bonds in total. So, it has no lone pairs. Sulfur is in group 6. It has only made 1 bond here. So, how many electrons would be left in sulfur? It has only contributed 1 electron here. You should have more electrons, 2, 4, 5, right? And then you also have nitrogen. Nitrogen, and this is very crucial. This is very crucial to understand. Nitrogen has 5 electrons in its outermost shell. It gave 1 here, 1 here, 1 here. So how many electrons are left? 2 electrons are left. Now look at it very carefully, very carefully. Look at this. Carbon had 4 electrons. All 4 electrons were shared by giving 1 electron to this bond, 1 to this, 1 to this, 1 to this. Good stuff. Nitrogen had 5 electrons. 1 was shared here, 1 was shared here, 1 was shared here. It has a lone pair left. Great. Sulfur had 6 electrons. It gave 1 electron here, and in total now it has 5 electrons left. But you haven't seen an electron alone right here. You always see electrons in pairs. So what has happened? See, that's why it is a negative charge. Why? Because an electron from the outside has come to the rescue for this sulfur. This is the reason why this has a negative charge. And this is how you need to deduce it as well. See, how would I know that sulfur is the fella due to which this negative charge is coming? Because once I wrote all the bonds and I showed all the lone pairs, I figured out that, hey, nitrogen has a lone pair. This has one odd number of electrons. And if it has an odd number of electrons and it has a negative sign, that means 1 electron came to its rescue to make it into a pair, right? So what's the bonding? Now you know. It's just carbon, single bond right here. It's a single bond right here. Here you have 3 bonds. So uno, dos, tres, 3 bonds here. And sulfur's bonds, lone pair, lone pair, lone pair. So lone pair, lone pair, and lone pair. What about this stuff right here for nitrogen? It's only 1 lone pair and only 1 lone pair. Boom. That's it. That's it, my dear friends. That's it. See how easy. Just need to use the brains. Question 13. Covalent bonds can be sigma or pi. Complete table 1.1 to show the number of sigma and pi bonds in nitrogen and to describe how the orbitals overlap to form the sigma bond and the pi bond. Now nitrogen is N triple bonded to N. I know the first bond is always sigma and the second 2 are always going to be pi's. So how many sigma bonds do you have in nitrogen? 1. How many pi bonds do you have? 2. How would the orbitals overlap? Sir, this is a head-on overlap. You can also call it a direct orbital overlap, right? So head-on overlap, and this is, write it completely. It's okay. You won't die if you write it a head-on overlap of orbitals. Right? Oh, great. It also says describe. So that's good. It's good I described it. It's a head-on overlap of orbitals. Please read the question carefully. Describe it. Head-on overlap. If you just write head-on overlap, 0 mark. 0 mark. This is where you lose marks in AS level. So describe it. Head-on overlap of orbitals. देखिए इसलिए मैं वैसे भी description कर रहा होता हूँ. Sideways, and this is what? Sideways overlap of the orbitals. Which orbitals, in fact? Of the p orbitals. Of the adjacent p orbitals, effectively. So it gives me 1 mark, 2 mark, 3 mark, 4 mark. Easy peasy lemon squeezy. Water is one of the products of B2O3 and NH3 as shown in reaction 2. Do I need to know this? No, absolutely not. Boron carbide is a hard crystalline solid that has a melting point. Oh, hard solid, and it's a non-metal bonded to non-metal, high melting point. Gives me a giant molecular vibe right here. Suggest the structure of bonding in boron carbide. Absolutely, it's giant molecular. Absolutely. Because see, these are non-metals. How in the world can a non-metal have a high melting point? Only if it is a giant molecular structure. So it's a giant molecular structure. And what's the bonding? It has covalent bonds. So it's a giant molecular structure with covalent bonds. So 1 mark for just this and this. That's crazy. NH3 reacts with HCl to produce NH4Cl. Now it's saying draw a diagram to show the ionic, covalent and coordinate. Coordinate is also known as dative bond present in the formula unit of NH4Cl. Now you know that when ammonium ion forms, how does it form? Well, you had NH3 already, you know, that looks something like this. This was my NH3, and this NH3 had a lone pair, and this lone pair right here, this lone pair went to form the dative bond with the hydrogen ion, and once it formed the dative bond, you had a 1 plus charge right here. And now that you have a 1 plus charge, you also have the chloride ion being bonded to it. That is how it's gonna look, right? So this is how it looks. I've shown the dative bond, I've shown you guys the hydrogens, and I've also showed you guys the chloride ion. So you could either show it like this, and because he's saying just draw a diagram, don't draw the shape, this is the very beautiful shape that I've drawn, or you could have drawn it, you know, just in the case of a 2D diagram. You could have also drawn a 2D diagram out of this. So just like this, you know, you could have drawn a 2D diagram out of it. Wouldn't really make a difference. A 2D diagram, a shape diagram, doesn't make a difference. Done. Easy peasy lemon squeezy, huh? Bismuth is an element of group 15 of the periodic table. Bismuth has metallic bonding. Draw a diagram to show the metallic bonding in bismuth. How do I show metallic bonding in bismuth? How do I show it? Oops, where did it go? I show it like this. Let me copy this. I've copied this fella, and let's show it for bismuth. Oh my god, what am I doing? Okay. What the hell? What the hell? Here you go, bismuth. Happy? Khush. Great stuff. Bismuth produces water to form bismuth oxide. A colorless gas that ignites with a squeaky pop also forms. Okay. Ignites with a squeaky pop also forms. Construct the equation for the reduction of water by bismuth. छोड़ दे. ये सवाल इधर नहीं आना चाहिए था. This question shouldn't be here. Although if you wanna look at it, you'll find this in chapter number 4. When we do chapter number 4, you'll kind of get a hang of how to do this. It's just construction for the reduction of water by bismuth. So bismuth H2O के साथ react किया, and it gives me Bi2O3. This is what it says. Bismuth reduces water to form bismuth oxide. So bismuth reacts with water. What would it give you? Squeaky pop sound is because of hydrogen. So this is what's gonna form, right? But this is just crazy. You know, for now, just let this be. This is the balanced equation for it. BiO3 is a yellow insoluble solid that melts at 1090 Kelvin. The molten compound conducts electricity. Deduce the structure and bonding of Bi2O3. What's the structure and bonding of Bi2O3? Well, you need to understand that in molten it conducts electricity. So it's an ionic compound. In molten it conducts electricity. So how do you deduce the structure? I'll say it's an ionic compound. Number one, why is it an ionic compound? Explain your answer. Why is it an ionic compound? Yes. Why? It's a giant ionic lattice. And why? I don't even have to write ionic compound. I can just talk about the lattice. It's a giant ionic lattice. And what's the bonding? The bonding is ionic bonding. And why is that the case? Because it has a high melting point. That's the first. And it can conduct electricity in molten state. That's the second. So, because it's pretty logical, huh? A high MP of 1090 Kelvin and conducts only in molten state. In this case, you know, conducts electricity in molten state. Obviously, aqueous में भी करेगा, but yeah, it's not soluble. It's saying it's insoluble. So that's why I've written the term only. Conducts electricity only in molten state. Why not aqueous? Because it's insoluble in aqueous. Yes, next. PCl5. It says in excess of blah, blue, blah, blue, blah, blue, blah. It's just saying complete to identify the shapes of each of these species. What are the shapes of these species? PCl5, what's the shape for it? Well, phosphorus is in group 5, no lone pairs. Cl5, always make the base first. So this is Cl, Cl. What about the 3 other chlorines? What about the 3 other chlorines? What about the 3 other chlorines? That's the trigonal base that you have, right here. Trigonal base. So this is Cl, that's Cl, that's Cl. And what's the shape called now? It's trigonal bipyramidal. Yes? So because of the trigonal base, trigonal bipyramidal. Yes. PCl6 minus. So P, and this is Cl4 tetrahedral. He's already given it to you. But what about this 6? I've drawn the 2 Cl atoms. What about the other 4? The other 4 should be the square base. The other 2 should be the square base. Right here. And in my opinion, it should have been called square bipyramidal, but this is called octahedral. What are the bond angles? It's 180 and 90 here, and it's 180, 90, and 120. Yeah. Now it's saying PCl5 reacts with J to form H3PO4. Identify J and state the type of reaction. This you'll learn in chapter number 4. What does it react with? It actually reacts with water. It reacts with H2O and then it forms phosphoric acid. And the type of reaction is called hydrolysis. Sir, how do you know? I know because I know. I know chapter 4. N2F2 molecule, देखो कितना simple है. There's literally nothing. I've taught you so many things and there's nothing here, because all of those things are tested in and going to be tested in the MCQs once you start doing the MCQs. So all of that conceptual build will be put to use in MCQs. The N2F2 molecule has a double covalent bond between its nitrogen atoms. This consists of a sigma bond and a pi bond. Complete figure 3.2 to show the dot and cross diagrams between N2F2. So how would I complete this? He's saying it only has a double covalent bond between nitrogen. So it's like N double bonded to N. And it's bonded to F and single bonded to F. How do I know single bonded to F? Because F is in group 7. It can only make a single bond, right? So this is how it would look, probably right here. Now, nitrogen was in group 5. It shared 1 electron here, 1 here, 1 here. So a lone pair is left. This nitrogen also has a lone pair. And since fluorine was in group 7, it gave 1 electron to the bond and it has 6 left. It has 6 left. So this is now what I need to plot right here. Each bond represents a pair of electron, a pair of electron, a pair of electron, and a pair of electron. So between N and F, a pair of electron, and these are the dots, 2, 4, 6. Nitrogen has a lone pair. This nitrogen also has a lone pair. And between nitrogen and nitrogen, you have what? You have electrons, and you also have between nitrogen and F, you have 1 lone pair, and here, you have 1 pair of bonding electron, and this is 2, 4, 6. Some students ask certain questions. They say, sir, because these are both nitrogens, can I represent them with crosses? Up to you. If you want, you can absolutely do this. It's dot cross, dot cross, dot cross, wherever you go. But if you want, you say, hey, these two are nitrogens, I just represent fluorine with dots, and can I represent these with crosses? Absolutely you can. You could also do it like this. I swear to God, it won't make a difference. You could do this like this. Or you could do cross, dot, doesn't really make a difference. Because see, electrons are the same. You just need to represent dot and cross to tell the examiner that the electrons are coming from this atom and that atom, this atom and that atom, this atom and that atom. That's it. Reduce the hybridization of N in N to F. What's the hybridization? Look at this. It has a lone pair and 1 electron cloud is here, 1 electron cloud is here, 1 electron cloud is here. So if you look at the electron for hybridization, always look at the electron geometry. What's the electron geometry? Right here, right here, right here. So it's trigonal planar. That's the electron geometry. Trigonal planar is what? 120 degrees sp2 hybridized. That's it. sp2 hybridization, because it's trigonal planar electron geometry. Yes, don't get me wrong, it's a bent shape. Yes, it's a bent shape. Yes, it's a bent shape. But that's the molecular geometry. What's the electron geometry? Think of this as a bond. If you thought of this as a bond, now what does it look like? One atom, the other atom. No lone pairs, that would be trigonal planar, right? So always talk from the perspective of electron geometry. So it's what? sp2. Or if you want to use certain tricks, taught by some teachers who want you to rote learn stuff, you could also do that. They say, hey, if you have one atom, you have to check out this atom. How many atoms is it bonded to? 2. It's bonded to 2 atoms. How many lone pair do you have? 1. And if you ever end up with 3, 3 means sp2. So if you want to do that, that's up to you. In my opinion, the electron geometry is easy to follow through. Draw a diagram to show the pi bond between the n atoms in N2F2 and describe how it forms. To show the pi bond. See, he's not asking you to show me the overlap. He's not asking you to show me the overlap. He's asking you to show me the pi bond. How do you show the pi bond? Like so. Like a kidney bean structure. This is the internuclear axis, and it's above and below. The pi bond forms above and below the two nucleus right here. So above and below the internuclear axis. That's how it forms. So how do I describe it to the examiner? Or that's why some teachers do discourage drawing this even when they ask about orbital overlap. Because in orbital overlap, this is acceptable and this is acceptable. But if you just show me the pi bond, then only this is acceptable, not this. So some teachers just tell the students to just draw this at all times. Although when they say draw orbital overlap, I'd rather you guys draw the other stuff, the orbital overlap. And when they say show me a pi bond, that's how you show the pi bond. So how do you describe the pi bond? Well, this pi bond forms, or how do I do it? Sir, when the pi bond forms and above and below the internuclear axis, or the plane, you could say, the plane of the nucleus, internuclear axis, right here, above with what do I say? English, can you fix my English, please? Pi bond forms above and below the internuclear axis with a sideways overlap. Overlap of what? Of the p orbitals. Here you go, examiner. Please don't just rely on the marking schemes. कि marking scheme में ये लिखा हुआ है तो यही होगा. No. Please write the descriptions. POCl3. How does POCl3 look like? I've even shown it to you. Remember when we were studying the structure? POCl3 tetrahedral. Yes, no lone pairs. Shows a similar chemical property to PCl5. Okay. Has a melting point of 1 degree Celsius and a boiling point of 106, which means it's simple molecular structure, not giant. If it was giant, it would have had a melting point of thousands and thousands and thousands. It reacts vigorously with water, forming misty fumes and an acidic solution. Explain the information in how the information in D suggests the structure and bonding of POCl3 is simple covalent. How do I know it's simple covalent? First of all, it's what? It has a low melting point and low boiling point. So low melting point and low boiling point suggests what? It suggests van der Waals forces, weak intermolecular forces of attraction, right? So I'll say, hey, low MP and BP suggests or is indicative of the fact that it has intermolecular forces. Weak, obviously. Weak intermolecular forces. Right? What about the second mark? The second mark you're going to understand in chapter number 4, which is reaction with water. If it's vigorously reacting with water, that suggests hydrolysis. And giant molecular structures don't undergo hydrolysis, right? So the second point is it is a vigorous reaction. There's a vigorous reaction with water, and therefore it's hydrolysis, right? And this represents that it's a simple covalent molecule. That's it. It suggests hydrolysis, or is indicative of the fact that hydrolysis is taking place. Done. POCl3 contains a double covalent bond between P and O. Complete the dot and cross diagram to show figure 1.1 in figure 1.1 to show the bonding of POCl3. Show the outer electrons only. I've always shown you the structure of POCl3. This is how it looks. This is how POCl3 looks like. Because phosphorus is in which group? It's in group 5. If phosphorus is in group 5, it'll share one. Oh, I killed a mosquito. It will share one electron here, one here, one here. What about the other 2 electrons? The other 2 electrons would be shared with oxygen. Why is it a double bond with oxygen? Because oxygens make double bond. It's in group 6. It's the octet rule which it's going to follow, right? So phosphorus will have no lone pairs left, but oxygen, it's in group 6. It'll have four electrons left in its outermost shell. It'll have 2 lone pairs because it was in group 6, gave 1 electron here, 4 are left. Chlorine, group 7, gave 1 to the bond, 6 are left. Give 1 to the bond, 6 are left. Give 1 to the bond, 6 are left. So that's what I need to draw. Each bond represents a pair of electron. That's a pair of electron, pair of electron, pair of electron, and 2 pairs of electron, right? So let's draw it. 2 pairs of electrons here, a pair of electron, a pair of electron, a pair of electron, and the lone pairs of oxygen, which is 2, and write it like this, 2, 4, and for chlorine, that's 2, 4, 6, 2, 4, 6, 2, 4, 6. It's just drawing. Easy stuff. The elements silicon, phosphorus, and sulfur are in period 3 of the periodic table. The melting point of silicon is this much. Why? What does this indicate? It indicates it's a GM, giant molecular structure. And the melting point is this, which indicates what? It's a simple molecular structure with weak van der Waals, with weak intermolecular forces of attraction. And here it has strong covalent bonds. It's saying, explain this difference. I've already explained it like a gajillion times now. I've already explained it a gajillion times, right? So how do you explain it, sir? You tell the examiner, hey, silicon is a giant molecular structure. It's a GM with strong covalent bonds. I'll not write it completely. You guys can do it on your own. Whereas, hence, more energy is required to, please always talk about energy. More energy is required to break these bonds. Break these bonds compared to versus sulfur, which is a simple molecular structure with weak IMF and thus requires less energy to overcome it. Overcome these attractive forces. See, my English may change. But the concept or the idea is always going to remain the same. Yeah. Easy. आसान है, मुश्किल है. Just last question. Lactic acid and pyruvic acid, oh my god, such difficult names, both contain 2 functional groups. Okay, it's organic chem, but don't worry, don't be scared. Let's see what the question says. Lactic acid forms hydrogen bonds with water. Okay, and complete figure 4.2 to show the formation of hydrogen bond between 1 molecule of lactic acid and 1 molecule of water. Now focus here. I want you guys to make the hydrogen bonds. Dekhiye, it's very important. See, this is a lone pair right here. Right? That's a lone pair right here, and a lone pair right here, and a lone pair right here. Great stuff. Now, if you had this lactic acid as your molecule, and you get another lactic acid, this lone pair would make a hydrogen bond with the partial positive hydrogen of the other lactic acid molecule, with the partial positive hydrogen of the other lactic acid molecule, all with the partial positive of water. This is what can happen, absolutely. And similar is the case here. It can happen right here, or it can happen at 180 right here. Just make sure it's 180, right? This is what's going to happen. Partial positive, partial negative. These are the pairs right here. Or what can happen is, see, this is also a hydrogen being bonded to one of the most electronegative elements on the face of planet Earth. So this hydrogen can actually form what? Can actually form a hydrogen bond right here. It can form a hydrogen bond with the water molecule, but not with the hydrogen, the partial positive hydrogen of water, but in fact the partial negative of water right here. This lone pair right here, lone pair, partial negative, whatever. So this will make it with O of water, and this O will make it with the H plus of water. What's better? It's better to show this right here. Well, it's the same thing over and over again. So this is also a hydrogen bond. That's also a hydrogen bond. It depends on what you want to do. You could make a hydrogen bond even right here, but then the hydrogen, this partial positive would be coming here of water, and this would be the O, and this would be the other H probably. Right? So you can make hydrogen bonds. If your concept is clear, you can make it here. You can make it with this. 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 Now it's up to you. What do you want to do? In my opinion, I'll just make the easiest, this would be the O of water, and these are the two H's of water. Just make sure to show the partial negative and the partial positive. Let me show both the lone pairs right here, and I'll show the partial positive right here and the partial negative right here. This is what I need to show the examiner. That's it. That's literally hydrogen bond. 3 marks for what? For nothing. 3 marks for what? For literally nothing. For nothing. These are my dashed, these are my hydrogen bonds. और इसमें क्या मुश्किल है? 3 marks. Do you know what these 3 marks are? For showing partial charges, for showing this bond, and for showing 180. That's it. This is what these 3 marks were for. और कोई सवाल हो तो बताएं. ये आपकी theory है यार. This is the theory for this chapter. Literally. How easy is this, guys? 21 questions हो गए हमारे. There are 100 questions in total. I'm going to do all. So 21 questions हो गए हमारे साथ हैं. आसान है कि मुश्किल है? Is it easy or is it difficult?